Hello, my name is Charles Burrows, and today we are going to be looking at diesel engine emissions and the mitigation systems that are designed to deal with the emissions. In this lecture today, I'm going to give a brief overview of internal combustion engines. I'm going to talk about diesel fuel, different characteristics of it, what its chemical composition is, and then I'm going to talk about the emissions that come from running a diesel engine. And from that, I'm going to talk about the emission mitigation systems. And then, using the knowledge from the emission mitigation systems, I'm going to do a demonstration on how a diesel particulate filter works. And so by the end of this today, you should be able to know what diesel fuel is and what emissions come from it, and then what we are doing to mitigate those emissions. There are two different types of internal combustion engines. We have spark ignition and compression ignition. Spark ignition engines are the engines that are most common in your vehicle. So most passenger cars are spark ignition engines. That's where they use gasoline and they have a spark to ignite the fuel. Then with compression ignition engines, those are all diesel engines. And so those are in more medium duty trucks, some light duty trucks. These are used more in Europe. And then also in heavy duty trucks, trains, and generators. And so diesel is the most common fuel for these compression ignition engines. And what's different from a spark ignition is that ignition is controlled by fuel injection and compression. So the combustion is driven by auto ignition, and there is no spark to start it. It just ignites on its own. So what happens is the fuel and air mixture is compressed, and then it ignites from the increase in pressure and temperature from the process of compressing the mixture. So with diesel fuel, it still comes from the same thing that gasoline comes from, except it is more refined. So it has a lower molecular weight, a lower viscosity, but greater cost because it takes more process to refine this fuel to make this fuel. Diesel fuel also contains sulfur, which results in the SOx emissions that we're going to talk about later. Diesel fuel is measured in what's called a cetane number. And so this cetane number determines its ability to auto-ignite. And so diesel contains two different chemical compositions. It's made up of N-cetane and heptamethylnonane. The N-cetane corresponds to a cetane number of 100, and the heptamethylnonane is represented by a cetane number of 15. So the normal cetane number that's used in passenger cars is around 40 to 60. And so a lower cetane number will result in more smoke and in rich running conditions, and a high cetane number results in more work to compress the fuel. So N-cetane and heptamethylnonane have the same chemical composition. It's just the way that the carbon and hydrogen is organized in the molecule. So when we do the stoichiometric combustion equation, we treat it as C16H34. And when we balance that, we'll get that the air-fuel ratio of the stoichiometric reaction is 14.9 to 1. And so when we're looking at the stoichiometric reaction, we don't have any oxygen at the end. We just have excess nitrogen because that doesn't react with the carbon and hydrogen. However, this would be very nice, but when you're doing combustion, you don't have perfect stoichiometric reaction. You're going to have a bunch of intermediate reactions. And with these intermediate reactions, we have different molecules that are being formed, like the emissions of NOx, the emissions of SOx, and then also we don't always have all of the fuel burn, so we're going to have emissions of unburned hydrocarbons, which is soot. And so we're going to talk about what drives those in the upcoming slides. So the first thing that we're going to talk about is the emissions of NOx. And so NOx is due to nitrogen in the air. There's a lot of NOx production in a diesel engine because you have a diffusion flame. But also with that, it's complex because of the unsteady mixing of fuel and air, and then the mixing of combustion products now more with fuel and air because you have flame propagation, and it doesn't all ignite at the same time. According to the Zeldovich equations, NOx is generated at temperatures above 1300 C. And so when we have the combustion reaction happening, we have the temperatures rising very quickly, and we get up close to the adiabatic flame temperature, which, I mean, we're not there because it's not adiabatic, but we're getting way above 1300 C when all these combustions are happening. And so what happens is we have N2 plus oxygen that turns into NO plus N, and then we have nitrogen and O2 that turns into nitrogen and oxygen. And then nitrogen also reacts with OH to make nitrogen and hydrogen. And so NO2 is present in the atmosphere and in acid rain. And also NO2 is the most prominent of the NOxes. So like the EPA will only look at the NOx that is NO2. And so it happens when we have NOx in the atmosphere is it can hurt the body's ability to absorb oxygen, just like carbon monoxide would, but it's only slightly soluble in water, so it only really affects infants and very sensitive people. Now, that still doesn't make it good, but it means that it's not quite as bad as carbon monoxide. And so NO2 reacts with O2 to create NO and ozone, and that's bad because that contributes to greenhouse gas emissions and the greenhouse gas effect because we don't want more ozone in our atmosphere. So SOx is interesting because sulfur we don't have in gasoline fuels. And so when you go to the diesel pump, you'll see that it's ultra low sulfur diesel. And that is because we don't want SOx to be created. SOx is also created the same way when you have the really high temperatures, just like nitrogen. And the thing about SOx is it's also treated as SO2 by the EPA. And so SO2 can hurt the respiratory system and it can make it hard to breathe. And then SO2 can also form other sulfur oxides and contribute to particulate matter emissions. So that's not good because we don't want to have just more soot in the air. And then SO2 can decrease the growth of trees and foliage, and it is part of what forms the haze that we see in the sky. So like in California sometimes when there's a lot of emissions coming from the waters and from all of the cars, it'll be harder to see through the sky. So we don't like SOx emissions either. Now, the most prominent emissions that people have talked about in previous years and currently are particulate matter. And so it's not always referenced as PM particulate matter emissions, but that's the soot, that's the dirt that we see in the air. Like we can see here with this beautiful blue Peterbilt truck, is putting a little bit of black smoke into the sky. Now, what's really interesting is that the big particulate from particulate matter emissions, that's not terrible because the big particulate, that'll fall to the ground, right? Because that has mass. So that'll become inert and go to the ground. The particulate matter is created by the engine running in rich or lean conditions. And so if the engine is not running perfectly stoichiometric, there will be more particulate matter. So with lean conditions, it makes rapid combustion difficult. So the normal flame propagation is affected. You're not going to have it combust really quickly. So that's going to create fuel pyrolysis and partial oxidation. So that's where we're going to have not complete combustion. And we're probably not going to make as much power because we're not burning how we should. Now with rich conditions that have excess fuel that doesn't combust. So we still don't have complete combustion because we have extra fuel. And so this fuel is either not able to completely mix because there's too much of it and there's not enough time for it all to mix to complete combustion. And so what happens here is we have the engine not running perfectly where it should. And so we're going to create more particulate matter emissions. And so another thing that can affect that is injector functionality, because the fuel needs to be atomized enough so that it can mix and combustion occur. Diesel is a liquid, and so that means that we need the fuel to be atomized, to be in the smallest droplets that it can be in, so that we don't have a long droplet time, so that we don't have to wait longer for the combustion process to occur. And so we have to make sure that the injectors are injecting the fuel in as small particles as possible, spreading them out as much as they can, so that when this combustion occurs, and it's very fast, that everything can burn properly. So the first emission mitigation system that we're going to talk about is EGR. This is exhaust gas recirculation. And so what the EGR system does is it puts some of the exhaust gases back into the intake of the engine. And the goal of this is to increase the amount of inert gas in combustion and to lower the peak flame temperature. And so because we have non-premixed combustion going on here, to have near peak flame temperatures. And so what we want to do here is if we introduce this inert gas, when we have the combustion process happen, that inert gas is going to take some of the energy and heat from the combustion reaction. And so the reason we're doing this is because we want to lower the temperature so that we have less NOx production. Because NOx production is based on the temperature. So the higher the temperature, the more NOx production we are going to have. So if we can put that exhaust gas back into the intake, that means we can burn it again. So if there is unburned hydrocarbons, we can get a little better combustion. And then also, the emissions are going to be decreased because the temperature is going to be lowered. And we don't want to have as much NOx emissions because NOx is bad for you, and we don't like that. The way that the EGR systems work is they take the exhaust gases and they go through a EGR cooler. And so what that does is that lowers the exhaust temperature so that you can keep the combustion temperatures as low as possible. And then the engine computer is going to control the EGR valve to control how much of that air goes back into the intake and how much of it goes straight through to the exhaust. As these systems have gotten more complex, more coolers have been added. There's a high pressure EGR system and then also a low pressure EGR system. All of this works together to continue to lower the combustion temperature to decrease the amount of NOx production. The next emission mitigation system that I'm going to talk about is DEF. DEF is diesel exhaust fluid. This is a mixture of water and urea, and what it does is it works with the selective catalytic reduction system. And so for the SCR to work, you need the liquid reducing agent to reduce it. So DEF is a combination of synthetic vehicle-grade urea and deionized water, and it's injected into the exhaust stream. And what it does is it breaks down the harmful emissions of NOx and turns it into nitrogen and water. And this can reduce the emissions of NOx up to 90%. The primary purpose of diesel exhaust fluid is to facilitate compliance with federal emissions standards. Another emissions mitigation system is the NOx traps. This is very similar to the three-way catalytic converter systems that are used in spark ignition engines. So there are precious metals within this trap that oxidize the NO to be NO2, and then the alkalis within the system absorb the NO2. And then this works in conjunction with the DPF filter because it's a trap, so it's going to trap all of that NO2, and at some point it needs to be burned off. And so once a regen is started, the regen causes the NO2 to be released, and then the rest of the precious metals within the system convert that NO2 into N2 and just oxygen. The most interesting part of the emissions mitigation systems on a diesel engine is the diesel particulate filter. So the diesel particulate filter we can imagine as a cylinder filled with straws, except that on one side, half of them are covered, and on the other side, the other half of them are covered. And so what happens here is the exhaust gases flow into this ceramic straw structure, and the particulate gets stuck in there. And then the rest of the air and exhaust gases go around the ceramic, go through the ceramic, and come out. And so you're left with just the particulate in the filter. And what it does is it catches all the large particulate and allows the very small particulate air to pass through. Now, because you're just having a filter and you're basically filling it with particulate, you need to clean it out. And so the way to do that is a regen. The old way that they did it is they would inject a little bit of fuel into the DPF system, and that would start basically a fire and burn off all of the particulate. But what would happen there is you could have thermal runaway, and then the whole thing would crack, and then you're out your whole exhaust system and you need to replace it. But now what we do is we just use the engine control module to increase the exhaust gas temperatures. And then what that does is that gets it hot enough in there that they burn off. We burn off the particulate. And so with this, it's so effective, so much so that newer diesel engines cannot even be emissions tested in the same way that they were before. So you can't just take all the exhaust gases and weigh them, because you used to have particulate and you could take that particulate and weigh it to figure out how much is this engine really putting out as emissions. But now you can't even do that. You have to take all the air that you did and you have to do a lot of tests on it to figure out exactly how much particulate is coming out. Now, what's really interesting about the particulate is that the big, large particulate that we saw in previous slide where there's that Peterbilt truck with all the black smoke, that falls to the ground. But because we're filtering it so much, we just have tiny particles. And what's happening with these tiny particles is that they stay airborne. So what happens is the particles don't fall to the ground because they don't have any mass. So we just breathe them in and they get stuck in our lungs. And so we don't have any of the big particulate. And yes, we're not polluting as much particulate matter because everything is tiny. But what we are polluting is small enough to get stuck in our lungs. And so there's a lot of different testing that's gone on with these emission systems. I mean, these have been around for a long time. And in diesel trucks, heavy duty trucks, they have a lot of different regulations on all the emission systems that they need to have. We're currently going towards an electric future, so I'm not sure how much will change about all these different emission systems, but research is still being done to figure out, is this the way that we should be doing it? Or should we be trying to have really big particulate instead of really tiny particulate? Because big particulate falls to the ground and goes away. So in this lecture, we learned about diesel. It has a cetane number, which says its resistance to autoignition, which is dependent on how much N-cetane and heptamethylnonane is in it. And then also we learned about the emissions. So like the NOx emissions, the SOx emissions, and the particulate emissions. And then we looked at what systems reduce that. So we have the EGR system and the DEF system, which reduce the NOx emissions. And then what those do is those still lower the temperature of the combustion, so that reduces the SOx emissions. And then we have the diesel particulate filter, which filters out all of the large particulate, burns it off so we don't have to have the diesel smoke, the big particulate, unburned hydrocarbons. And so diesel engines are really cool. They're still going to be used a lot today. As we can see in this slide, we have a nice Peterbilt 389X, and we're still using them. We're still doing more research. CARB and EPA are still coming out with more regulations about how much emissions we can have, different systems that we need to reduce those emissions. But it's an never-ending research to try and reduce our emissions, reduce what we're doing. But diesel engines are really cool, and they're going to be here for a long time still. So the demonstration that we're going to do today is a demonstration of how a diesel particulate filter works. The setup that we're going to have is a fire ring and then essentially a tomato plant ring to hold the paper on top. And the paper on top is going to describe the diesel particulate filter. And that's going to catch all of the particulate as it floats up, but then it's going to let the exhaust gases to go through and catch the particulate. Now, the safety that we have here is we have a bucket of water nearby. We're in a green lawn that my dad let me use because he needs to replace the grass anyway. But we have water nearby. We're going to keep safe. And then once the paper particulate filter is full of soot, we're going to increase the temperature of the fire, increase the height of the flame so that we can burn off the paper and simulate burning off all of the soot that would be done during a regen in a diesel vehicle.